Hello, Algebra 2 CP. Hopefully, you're having a great day so far. You may notice a little bit of a change of scenery, a little bit of a different layout coming at you today. I did decide to start doing videos from home now as opposed to in class, just so I don't have to dismantle my live teaching setup every time I want to do a video. So that's why it looks like a little bit of an upgrade here and a little different background behind me because I'm sitting in my house. But I'm still going to teach you math and it's still going to come to you all the same. Today, what I'd like to do is I'd like to talk to you about the powers of I. And just to recall, I was defined to be this imaginary number equal to the square root of negative 1. And sort of the purpose of using this value of I is the fact that when we encounter a negative square root, we don't just have to like go home and sulk and stop our problem. We can just isolate that problematic component, pull out that I, and then just continue about our day. We don't have to like go back to square one. All right. So that's really the benefit of using this value of I. Now, I, when you start applying exponents to it, becomes a very, very interesting case. So before we get into all the meat and potatoes of that, what I do want to do very quickly, it'll take maybe about 5 minutes, is I do want to review with you the basic laws of exponents from Algebra 1. Maybe something you already know, but just in case it's not, it should be a nice little refresher as a nice review. And I think it's necessary too, of the laws of exponents, because we are going to be using the laws of exponents when we now apply this value of I to them. So if we don't know the laws of exponents in the first place, that's going to make this a little more difficult. Just a little quick FYI. I don't know if you've ever actually been given the definition of an exponent, but an exponent is something that indicates repeated multiplications. That's all an exponent is. It's really just shorthand for repeated multiplications. A good example of that, we know that 2 to the third power is equal to 8, correct? Because 2 to the third means to take 2, so I'd say because. This means to take 2 and multiply it by itself 3 times, and 2 times 2 is 4, times another 2 is 8. All right, so that's really what an exponent is all about. I'm sure you knew that already. When we're adding and subtracting values that contain exponents, so just very quickly, when we're adding and subtracting values that contain exponents, for example, 2x to the fourth minus 3x to the fourth, because those variables have like exponents, they are considered to be like terms. Just like if it was 2x minus 3x, it would be treated the same way. I have 2x to the fourths minus 3x to the fourths. So how many x to the fourths do I have? I have negative 1 of them, x to the fourth. Okay. If I have exponents that are unlike, for example, 5x to the third plus 2x squared, we can't combine that into some hybrid term. This is x to the third, this is x squared. Those are different. They're unlike terms. This cannot be combined. Okay, just so you're aware. That cannot be combined. Okay. When we're multiplying and dividing exponents, what do we do? Well, multiplying and dividing I think is a little more interesting. If I have x to the fourth times x to the fifth, well, think about what that means. X to the fourth means I have x times x times x times x, right? Multiplied by itself 4 times. X to the fifth means I have x times x times x times x times x 5 times, right? So what this really expands out to be is we have x to the fourth, x times x times x times x, right? There's your x to the fourth written out. This is why we use exponents, so we don't have to actually write that out every time. And here's our x to the fifth, 3, 4, 5. And so when we're doing x to the fourth times x to the fifth, how many x's do I actually have in a line all being multiplied together? I have 9 of them. So x to the fourth times x to the fifth is x to the ninth. You may have heard the age-old expression in Algebra 1, when you multiply the same base, you add the exponents, which is absolutely 100% true, and this is why you do that. You do that because it just ends up being this whole row of exponents written out. Okie doke. So another example, just to show you, if I had y to the 10th times y to the third that would be equal to y to the 13th. Because this would be 10 y's all being multiplied together, and this would be 3 y's being multiplied together. So in total, you would have 10 plus 3 of them and 13 of them. Okay? When we divide, the same pattern kind of holds true. I feel like a lot of Algebra 1 students are really comfortable with this. They're like, oh yeah, multiply the same base, add the exponent. But then when we get to divide, they're like, I don't know what to do. But it's really the same thing. If I had x to the 8th divided by x squared, okay? A lot of students will mistakenly say that this is equal to x to the 4th because they'll say it's 8 divided by 2, which is 4. Seems reasonable, but not correct. Think about, again, what this actually expands out to. X to the 8th is 1, 2, I should have picked a smaller number, 3, 4, 5, 6, 7, 8 x's all being multiplied together, all divided by x squared. Well, x squared is 1, 2 x's being multiplied together. So look what happens. X divided by x is going to cancel out. That's equal to 1. X divided by x goes away. And how many am I left with? Well, I'm left with 6 of them, or x to the 6th. So it's accurate to say that x to the 8th divided by x squared is x to the 6th. And you may notice the pattern already that same with multiply. When you multiply the same base, you add the exponents. Well, when you divide the same base, you subtract the exponents, right? Do you see that? X to the 8th divided by x squared is just x to the 8 minus 2 power, or x to the 6th, because those two x's cancel out. All right, just to show you another one really fast. If I did x to the, let's do x to the 10th divided by x to the 3rd, kind of like our multiplying example up here, well, that's going to be x to the 7th. Because you could probably picture the fact that there would be 10 x's in the numerator, 3 x's in the denominator, 3 of them would cross out, and you'd be left with 7. All right? So when you multiply the same base, you add the exponents. When you subtract the same base, or when you divide by the same base, you subtract, rather. Okay? Multiply, add, divide, subtract. Very good. One more thing that you see in laws of exponents all the time is you see a power raised to a power. That's a thing that comes up pretty frequently. So if I have something like this, x to the 5th to the 3rd, right? X to the 5th all raised to the 3rd power. Again, it's beneficial to think about what this actually means. X to the 5th to the 3rd means essentially I have 3 sets of x to the 5th. I have x to the 5th, here it is, 3, 4, 5, multiplied by itself 3 times. So that means I have another x to the 5th in the same multiplication chain, and another x to the 5th in the same multiplication chain. And so how many x's are there altogether being multiplied? Well, there's 3 by 5, or in other words, x to the 15th. So when you raise a power to a power, you multiply the exponents. Okay? X to the 5th to the 3rd is the same as x to the 15th because that's 5 times 3. All right, just to show you another one really fast. If I did y to the 6th to the 8th, well, that's going to be 8 groups of y to the 6th. I'm not going to write that all out, but that would be y to the 48th. 6 times 8. Okie doke. Just a couple quick miscellaneous facts about exponents. When we have anything raised to the first power, anything raised to the first power is just equal to itself, right? So x to the first is just equal to x. That everybody should know that, but just to make it clear that any number raised to the first power is itself. So when you actually see just a regular old x in an equation, it is secretly an x to the first power in there. Also, anything raised to the 0 power is equal to 1. There's actually a wicked cool explanation as to why that's the case. I'll do it. It'll take just about a minute. But let me continue listing the miscellaneous facts first. We have x to the minus 1 power. If you do x to the negative 1, that's the same as 1 divided by x, because instead of repeated multiplications, you are now doing a repeated division if you're a negative power. We will talk about that a lot more later in the year, but just throw it out there so you see it now. And the last miscellaneous fact is x to the 1/2 is another way to write the square root of x, which is kind of cool because 1/2, it's almost like we're doing the opposite, or we're going backwards, right? So that's pretty neat. All right, super quick explanation as to why anything to the 0 power is 1. You ready? Then we'll get to the powers of I promise. Okay, super quick explanation as to why anything to the 0 is 1. Consider, I'll use the powers of 3 in this example just to show you, so the numbers don't get too big and out of control. But you could use any power and it'll work. Powers of 4, powers of 5, but I'll just pick powers of 3 for the sake of picking one. Ready? Let's suppose that we know that 3 to the 4th is 81, which is true. 3 to the 4th power is 81, but I don't know what 3 to the 3rd power is equal to. I'd be like, I don't know, what's 3 to the 3rd? Well, what I could do to get from 81 down to my mystery answer of 3 to the 3rd is I can take 81 and divide by 3. Right? Because if I do that, I'll divide out one of those powers of 3's, and I'll get down to only having 3 of them instead of 4 of them, and that would equal 27. Well, now I could take that and divide again by 3, and now have 9 left over, because that would be equal to 3 squared. Well, what's 3 to the 1st? 3 to the 1st, I'm just going to follow the same pattern. If I divide by 3, I get 3 to the 3rd. If I divide by 3, I get 3 squared. Let's take this, divide by 3, we get 3 to the 1st. And then the question comes up of what is this? 3 to the 0. Well, we have to keep following the pattern. It's not just going to suddenly abide by some new rule. To get from here to here, I divided by 3, I divided by 3, I divided by 3. We would divide by 3 one more time and take a look at what we get, 1. And that will be true for any single value that you pick. You'll always have this situation where you're doing the number divided by itself, and you get that this value of anything to the 0 power is 1. Okay, pretty neat. A cool pattern of this, by the way, is if you actually keep going, well, what's the pattern here? You'd have 4, 3, 2, 1, 0, 3 to the negative 1. If we take 1 and divide it by 3, it's 1/3, which is exactly the rule I said here. Anything to the negative 1 is 1 over itself, which is pretty cool. So you see that actually in action as well when you look at that pattern. Really, really cool stuff. All right, very good. That was a long time on the laws of exponents, but I think it's important to actually review that. Hopefully no questions on that. Let's now actually throw in some i's and see what connections we can make. All right, so now that we've done a nice review of the laws of exponents, let's actually start to introduce this concept of I. Ready? We know that I is equal to the square root of negative 1. Right? We know that. That's the fact that we've defined. We've defined this value of I to be the square root of negative 1. So it's fair to say that I raised to the first power is equal to I. Correct? I feel like that's not rocket science. Any number raised to the first power is itself, so I raised to the first is itself. What about I squared? What if I do I squared? Well, think about what that would be. I is the square root of negative 1, so that would be the square root of negative 1 squared. And so I squared, the square root and square would cancel out, would actually equal negative 1. Which is super cool. I square, taking this imaginary number and squaring it, you get a real number. Really cool stuff. Whatever you want to do in your notebook to make this fact stand out, all of these powers are important, but I feel like that one comes up most of all, in addition to I to the first. Just knowing that I squared is negative 1 is a super important fact. All right, so make sure to highlight that. Well, what about I to the third? Well, think about how we can break down something like I to the third. You could say that I to the third is the same as I squared times an additional I. Right, that's true. That would make 3 of them. Well, I squared we just established up here is negative 1. So that would really be equal to negative 1 times I, or negative I. So we can say I to the third is negative I. All right. I to the fourth, well, we could write I to the fourth as I squared times I squared, right? Because that would make 4 of them. I have 2 of them, and then 2 more would make 4. Well, I squared we just said was negative 1, and I squared again is negative 1, so I to the fourth is 1. Cool. And the fact that we get 1 there, 1 makes this pattern very, very interesting, because take a look at what's going to happen with I to the fifth. Well, I to the fifth, I can say is I to the fourth times I. But I to the fourth, we just established to be 1. So I to the fifth is really 1 times I, which is I. The same as I to the first. Weird. I to the sixth is the same as I to the fourth times I squared. Right? You'd agree with that. Those are the same number of i's. Well, I to the fourth is 1. I squared, we established up here, is negative 1. So I to the 6th is also negative 1. I'll do a couple more. I to the 7th, well, I to the 7th we could rewrite as I to the 4th times I to the 3rd. And I to the 4th we know is 1. So we established I to the 3rd is negative I. So I to the 7th we could say is also negative I. Really cool. I to the 8th, maybe coolest of all, we could say is I to the 4th times another I to the 4th, because 4 and 4 would make 8. I to the 4th is 1. I to the 4th again is 1, and 1 times 1 is 1. Start to notice something pretty cool here. A little bit of a repetition, right? So we can say that we have I to the 9th. Well, I to the 9th should follow the same pattern, and that would be I. I to the 10th would be negative 1. I to the 11th would be negative I to the 12th would be 1. And this pattern would repeat every 4 exponential powers. You're probably noticing that already. So this pattern, what's called a cyclic pattern, not cyclic as in sick, like feeling ill, cyclic as in cycle. This cyclic pattern repeats every 4 exponential powers. So just to make this little chart for you, as far as the exponent and the value, if you have I to the 1st, I to the 5th, I to the 9th, and so on, we get that that's all equal to I. If we have I squared, I to the 6th, see how we're counting up by 4 every time? I to the 10th, etc., that's all equal to negative 1. I to the 3rd, I to the 7th, I to the 11th, again, we're counting up by 4 every time, and so on and so on and so on, is equal to negative I. And I to the 4th, I to the 8th, I to the 12th. Notice every time we get a multiple of 4, we get 1. Pretty cool stuff, right? So with that knowledge, we can actually now evaluate I raised to any power. And I want to show you a couple tricks as to how we can do that. All right, hopefully we're doing good so far. Okay, so consider now a couple examples like this. Kind of separate this here. Consider a couple examples like this. Ready? How about I to the 32nd power? How could I actually evaluate what that is? Well, we know that I follows this cyclic pattern of repeating every 4 powers. So we just pretty much have to find its position in the table and see, like, okay, where are we actually located? Well, there's a couple ways we could do that. Number one, you could count. You could physically count and just say, well, let's I to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. And you could just count up, 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 up. And you would eventually reach the fact that I to the 32nd would fall here and be equal to 1. That's an okay strategy for smaller numbers, but you could probably imagine that as things get larger, that strategy would probably fall apart. All right. So another way to think about it is you could say, well, I to the 32nd, 32 is a multiple of 4, which is true. And the fact that 32 is a multiple of 4 means that, ooh, it must fall here in the chart, and so it would be equal to 1. That's a little bit more sophisticated of a way of doing it now. And notice the reason why we're choosing multiples of 4 as opposed to random numbers is because this pattern repeats every 4 times. All right? So you could just say, oh, well, I to the 32nd is a multiple of 4, so I to the 32nd is equal to 1. How about something that's not a multiple of 4, though? How about like I to the 22nd? Not a multiple of 4. Well, what you could do is you can count to the closest multiple of 4, figure out what that is, and then just see how many additional spaces we need to go in order to get to my target. So for example, we know that I to the 20th, 20 is a multiple of 4. 20 is the closest you can count without going over 22. So from 20, we could then proceed and say, well, I to the 21st would land us back in this top spot, and I to the 22nd would land us here. So we can say I to the 22nd is negative 1 because this would just cycle around. Okay? Very good. Question about that? Can you get out of my video? My fiance's coming in trying to make a cameo. Get out of here. I'm doing math. I'm teaching people things. Yeah, yeah, yeah. Keep walking. All right, anyway. Anyway, sorry about that distraction. Any question about that? All right, let's keep going. Okay. How about with that strategy then? So we could count to the closest multiple of 4 and see where we are. How about I to the 19th? Well, I could say, well, what's the closest multiple of 4 to 19? 16, right? Without going over, if I count by 4s, 4, 8, 12, 16. I to the 16th would put us here. That means I to the 17th would put us here. 18 would put us here. And 19 would put us here. Okay? So that would be negative I. Bam. Quick. Instead of actually counting up to, you could also count backwards. And you could say, well, I to the 20th would be here. So actually one spot behind that, like almost think of the pattern in reverse, would go to here. Okay, so that's another way you could consider it as well. All right. But now, what happens if we have a larger number? Right? How about this? Oh boy. Some super big jumbo number. Okay. 8,675,309. How do we find I raised to that gigantic power? Well, what we can do is a couple things. Number one, we can count. I think that strategy is kind of out. We could also try to count by 4s. That might be a little better, but still out. But we do also have a handy-dandy calculator. And what we could do is we could take this number, divide it by 4, and actually see what the remainder would be. Because that remainder would tell us how many positions away we are from going in evenly. All right? So if I did that big number divided by 4, 8,675,309, divided by 4, we get that it's equal to something 0.25. And this remainder of 0.25 means that there was 1/4 left over. Right? So I took this big number, I divided it by 4, and the fact that we got a remainder of 0.25 means there was just 1/4 left over. So there being 1/4 left over means that, oh, well, from my multiple of 4, I need to advance one position to get there, and so we'd be able to say this is equal to I. Okay? So if we divide this number by 4 and we see the remainder of 0.25, 0.25 is an indication that there's 1/4 left over. So from my multiples of 4, I had cycle one position in the table, and I end here. Okay. Likewise, a remainder of 0.5 or 0.50 would mean that we are at that position because I would be at my multiple of 4 and cycle 2 spots. A remainder of 0.75 would mean that there's a remainder of 3. I would be at my multiple of 4 and cycle 3 spots. And no remainder, well, that would mean that it is a multiple of 4. So it went in evenly, and I would be at that position. It would be equal to 1. So with that knowledge, we can now actually tackle any big number that you can throw at us, any scary number. We'll give Cumberland a shout out here if I did I to the 02864 power. Well, what I could do is I could take that big scary number. You obviously don't need the 0 in front, but if I did 2864 all divided by 4, bam. We get that it goes in evenly, meaning there's no remainder, meaning that I raised to that big giant power is equal to 1. Pretty neat. Pretty neat. Another really cool shortcut and trick that you could actually do for this type of stuff is you could actually just look at the last 2 digits of a number and just consider that number. Notice the previous example, 9 divided by 4 gets me that 0.25, the same remainder. 64 divided by 4 gets me that no remainder from the previous examples. Okay. The reason that works out actually is because 100 is divisible by 4. So you can extract all the factors of 100 from here and just be left with that 64 in the end. Neat stuff. All right, to close out, I know we've been at it for a while. Let me show you that we can, of course, mix in the laws of exponents that I introduced before with these powers of i's. Like this, for example. I to the 13th times I to the 10th. Well, there's 2 ways that you could really work this out. The first of which is you can, so I'm going to say there's really 2 strategies. Okay. The first strategy, you can really just combine them together right at the start. And we can say, well, I to the 13th times I to the 10th is the same as, well, same base. Let's add the exponents, 13 plus 10, so I to the 23rd. And then we can just say, oh, well, where does I to the 23rd fall on my chart? The closest multiple of 4 without going over is 20. That means I to the 20th would be here. Follow the cycle. I to the 21st would be here. 22nd would be here. 23rd would be here. We could say it's negative I. Okay? Of course, instead of counting, you could also just jump straight to the calculator. But I do always encourage not using a calculator whenever possible. Okay? The other strategy that you could actually do is you could solve it independently. You could figure out what each one of these things are. We could say, oh, well, I to the 13th would be I, because it falls one position after I to the 12th, so I to the 13th would be up here. I to the 10th, well, I to the 10th is actually listed here. I to the 10th would be right here, negative 1. So we can evaluate each of these things independently and say, oh, well, I to the 13th is I to the 10th is negative 1. Negative 1 times I is negative I. And so we end up at the same position. All right. Same thing is true when you have a power raised to a power. So consider something like this. If I did I to the 5th to the 3rd. Again, sort of two strategies to handle this. I think this time simplifying is actually much easier. I always like simplifying first, actually. That's the one that I always go with, but there's nothing wrong with doing them separately. Nothing wrong with it. I just always like to combine them together so that I'm only dealing with one thing as opposed to dealing with two things, but however you want to do it is fine. Well, we could say the first thing we could say is this is I to the 5th to the 3rd is a power to a power. We talked about on the back side of the sheet, the power to a power means to multiply. That would be I to the 15th. And using our chart, I'd say, well, I to the 15th would end up here, because if I to the 12th is here, I to the 13th would be here, 14th would be here, and 15th would be here. Negative I. Done. Alternatively, you could say, well, let's evaluate that inside piece of I to the 5th. We could say, well, I to the 5th falls here. That's I. And now we have that raised to the 3rd power. Well, I to the 3rd we know is negative I. Okay? So there's a couple different ways that you can actually go about it. I always like to do the simplify first, because I think simplifying first, sorry, I meant to make that an I, not a 1. Negative I, right? Just like over here, negative I. Okay? I think that simplifying first is always better, because then you're only working with one value as opposed to working with multiple values. For example, think if it were like 3 things being chained together in a multiplication. I'd much rather try to condense it first, then figure out what you're actually dealing with. But that's entirely up to you. That's entirely up to you. All right. All right, I think we've gone on for long enough about powers of I, but there's this really cool cyclic relationship, this cycle that exists. You can evaluate I raised to any power by just following this pattern. If you figure out where it falls in this pattern, figure out where the multiples of 4 will lead you, then you can figure out I raised to any power. All right, just a quick little review. We talked about the laws of exponents as well as a bunch of other things about them. And we talked about how to calculate I raised to any power. Remember this cycle. This cycle is incredibly valuable and useful. It comes up a lot, especially this I squared fact. Comes up a whole heck of a lot. Remember that if you actually are dealing with a number that you don't know where it falls in the cycle, you could always use your calculator, divide by 4, and check the remainder. Okay? The laws of exponents also apply, where if we're multiplying the same base, we add. If we're doing a power to a power, we multiply. And if we were dividing, we would subtract as well, and follow all those same laws of exponents. All right, guys, thank you so much for listening. I'll try to make the future videos a little shorter, but there was a lot of background information I wanted to give here, and hopefully you'll learn something valuable. I will see you guys next time. Thank you so much for your attention and focus. Try those practice problems on Google Classroom, and have a fantastic rest of your day. See you later.